I'm Shogo Hanayama, a first-year master's student at Keio University in Japan. Let me begin my presentation. As a background, rings are prevalent accessories. Because of their small size and social acceptability, rings have attracted attention for cashless payment, live logging, and input operations. There are actual commercial examples. Some ring-shaped input devices allow two-dimensional input with the palm of the hand or using thumb on the index finger. These devices provide tactile feedback and enable eyes-free input, but users of these ring-shaped devices often need to wear the ring-shaped device in the correct direction of rotation on their finger to maintain accurate input coordinates. To improve the usability of the ring-shaped input device, we designed the SkinRing. SkinRing consists of 8 photoreflective sensors attached to a ring that irradiates infrared light onto the finger. The values of the photoreflective sensors change in response to hand movement. Furthermore, the SkinRing is a compact ring-shaped device that enables gesture input on the side of the finger independent of wear direction. Since typical ring-shaped input devices cannot identify the wear direction of rotation, it is necessary to be aware of the wear direction. Therefore, we propose manipulation of hands opening and closing to identify the wear direction of ring rotation, which provides consistent gesture identification, even when the ring is rotated. So the SkinRing eliminates the need to adjust the direction of rotation of the ring when wearing it, as long as it is calibrated. Next, I will describe the principle of skin deformation detection. When the hand is opened or closed, or when the thumb traces the side of the index finger, the skin near the ring undergoes deformation. A photoreflective sensor emits infrared light, and the amount of reflected light varies depending on the distance between the object and the sensor, allowing the distance to be measured. The skin deformation is detected by measuring the distance between the photoreflective sensor and the skin of the finger for calibration and gesture identification. Previous study, eye-ring is similar to our device, but the gesture identification isn't implemented in it. Regarding the hardware design, 8 photoreflective sensors are attached to a ring made by a 3D printer. These sensors emit infrared light to the finger. Photoreflective sensors are mounted at equal intervals around the ring to ensure that input is independent of wear direction of rotation through calibration. We designed the two sizes of devices. The diameter of the large size is 21 mm and the diameter of the small size is 19 mm. The sensor values acquired from the photoreflective sensors are transmitted to a laptop using an Arduino Pro Mini. Next is identification system. Since sensor values change significantly when the hand is opened and closed, the wear direction of ring rotation can be predicted by performing hands opening and closing movements twice. Then, the order of the subsequent gesture sensor data is rearranged based on the calibration result, and gestures can be identified with a high degree of accuracy. So, in our system, two levels of identification are used. The first is calibration. In this study, the hand is opened and closed twice from the closed state to acquire 8 sensor data as a calibration. After standardizing the time series data, the data is divided into 10 parts and 5 features are extracted for each part. The direction of rotation in which the ring is worn is identified with a random forest. The second is gesture identification. After calibration, gesture is performed to acquire 8 sensor data. After standardizing the time series data, the sensor data is reordered to match the wear direction of rotation predicted by the calibration. the gesture data is divided into 10 parts, and 5 features are extracted for each part. Finally, gesture is identified with a random forest. This system can reduce the effect of rotation of the link and enable gesture identification independent of where direction of rotation. Since the calibration process can only identify 8 discrete wear directions of rotation, it cannot predict the exact wear direction. So, in gesture identification, we effectively utilize reordering of the 8 sensor gesture data for more accurate identification. As training data, we use not only the sensor data reordered to the actual wear direction, but also the sensor data reordered to the 2 adjacent wear directions, forward and backward. In the identification of test data, in addition to predicted probabilities for the sensor data reordered to the predicted wear direction, the predicted probabilities for the sensor data reordered to the 2 adjacent wear directions were calculated. Then the gesture with the highest probability among all was chosen. We conducted 3 experiments. First, we evaluated the gesture identification accuracy when participants wore the SkinRing in one wear direction. Second, we evaluated the identification accuracy of the wear direction of ring rotation predicted by the calibration. At the same time, we also created the calibration model for each individual to be used in experiment 3. Finally, we evaluated the gesture identification accuracy when participants wore the SkinRing in the 8 wear directions. This experiment includes purpose of this study. A user study was conducted on 10 participants. They wore the SkinRing on the index finger of their right hand in the experiments. There were 8 male and 2 female participants, all of whom were right-handed. The ring used varied between small and large sizes according to the size of the user's finger. 3 participants used the large size and 7 participants used the small size. All experiments were conducted indoors. In the first experiment, we fixed the direction of rotation of the ring in direction 0 with the wire pointing towards the back of the hand as shown in the left figure. A total of 9 gestures shown in the right figure were used. In the experiment, one set consisted of performing all 9 gestures one time each, and participants performed 10 sets of this. We performed within user and without user cross-validation on the 10 sets of sensor data acquired. As a result, the average within user identification accuracy of 9 gestures was 90.7%, and the average without user identification accuracy of 9 gestures was 67.2%. The results for each user are shown in the right bottom figure. These results indicate that without user identification is much more difficult than within user identification. In the second experiment, we evaluated the prediction of the wear direction by the calibration. Calibration movement is the hands opening and closing twice, shown in the left figure. Participants performed the calibration movement 3 times for each of the 8 wear directions of ring rotation, shown in the right figure. We performed within user cross-validation on the acquired sensor data. As a result, the average identification accuracy of 8 wear directions was 58.8%. The confusion matrix is shown in the right bottom figure. The average distance error was 0.413. The average distance error means the average distance between the predicted label and the correct label when the distance between the label and the adjacent label is set to 1 for each wear direction. Moreover, when not only the actual correct label, but also the both neighboring labels were considered as correct labels, the average identification accuracy was 99.2%. These results reveal that calibration can make a prediction including the adjacent direction of rotation labels, with a probability of almost 100%. In the third experiment, we evaluated the gesture identification accuracy when participants wore the SkinRing in the 8 directions. Since the gestures in direction 0 were reordered in experiment 1, were recorded in experiment 1. Participants performed 3 sets of gestures in each of the remaining 7 directions. One set consisted of performing all 9 gestures one time each. We performed within-user cross-validation on the 3 sets of sensor data for the 8 directions, with and without calibration, for each user. One set of gesture data for one direction was used as test data, and gesture data other than the test data were used as training data. The calibration model used was the within-user model created in experiment 2. The results showed that the average identification accuracy of 9 gestures was 87.8% with calibration and 76.0% without calibration. The identification accuracy with and without calibration for each user are shown in the right bottom figure. The results show that calibration facilitates gesture identification independent of the direction of rotation of the link. As future work, device versatility can be expanded. We can make more sizes of devices. It is also possible to wear it on the middle finger, and the SkinRing can be used for pointing. For practical use, a lock function should be added to prevent users from unintended input while wearing the link, and we should enable more comfortable input by making the device wireless. This is a summary slide. Thank you for listening.